Okay, recording, share screen. Today for the lecture portion, we're going to do a brief recap of what we've talked about the past two lectures. Since you guys are right in the middle of lab 3, doesn't hurt to have a refresher. But then we're also going to talk about different ways that you can measure frequency response function using convolution more quantitatively than what we've discussed so far to actually remove the effect of the instrument response function. And also discussing other types of filters that you may encounter in addition to the low pass, high pass, and band pass filters. So yeah, what I just laid out here. With the getting more quantitative with convolution, we're going to give an example first of what happens when you convolve two Gaussian functions, and this plays an important role in error propagation analysis. So that's why we're going to work with that Gaussian example, and then also how you can then use that to remove the effect of the instrument response function. So to recap some of what we've discussed in the past two lectures, I'm just going to be using animations and PowerPoint. Since it's all recap, all this stuff is going to be the same as what we've written in the previous notes. So that's why I'm going to go quickly through it using the animations. And you can always refer to the YouTube video if you want to see these written out again. But again, they're in the notes that I've uploaded on Canvas. They're also in the previous lectures and the YouTube videos as well. And I forgot to upload the notes. I'll upload them out after class. Let me make a note of that for these last 3 points here. Okay. So again, we're talking about filters. We're working with filters in lab 3, where the importance of using filters is you can remove unwanted components from your signal, be it noise, be it contributions that are at a high frequency or low frequency from other things in your measurement. And to understand how your filters respond to different frequencies or different time areas, we measure the instrument response function in the time domain or the frequency response function in the frequency domain. To understand how your input signal is modified by that filter to then produce your output signal. So we have this little block diagram here sketched out that your filter would be in between your input signal versus your output here, where I think in this cartoon, we're removing some high frequency components with the signal in this cartoon sketch. We established that the instrument response function, if you take that in time, you can perform the Fourier transform to get your frequency response function in frequency, hence why you guys studied for today's quiz to understand what the influence of taking a Fourier transform is quantitatively for given signals. We then introduced a new mathematical concept of convolution, that your output signal is then the convolution or how your input signal and your instrument response function affect each other to then produce that output that you actually observe on your oscilloscope, on your KDMM, or whatever tool that you're using to measure the output there. We described convolution quantitatively, mathematically, that we use this asterisk notation for two given signals in the time domain. If you take their convolution, it's the same as multiplying them, integrating them as they shift past one another for this synthetic variable of t prime or time that doesn't show up in your output in the time domain. So with the nice animations, as opposed to my sketches showing a square pulse and an exponential convolving with one another, the yellow area under the curve, that's going to be that multiply and the integral there. Last week, we established that while we wrote out what the convolution is in the time domain, that taking the Fourier transform, convolution in the time domain is equivalent to taking the product in the frequency domain. So it's typically much easier to just multiply two signals than taking the convolution. Hence why many times we're looking and establishing the frequency response function instead of the instrument response function. And then using Fourier transforms to shift in between those two, but if you want to manipulate your output here, working in frequency can be more useful. And we'll see that today when we talk about deconvolution or removing your response function. It's easier to work in the frequency domain there. We then went into the specifics for the different filters, low pass filter, high pass filter, band pass filter, where we establish what components are in each of those circuits in the most simple sense, that an RC circuit for low pass and high pass filters sketched here. And to get at Michael's question from last week, if you guys didn't look at the discussion or the announcement, I forget where I put it on Canvas, it has to do with the fact that capacitors, if it's a low pass or high pass, where it is in the circuit will lead to those capabilities, because capacitors have a frequency dependence. And that's what we call this reactive capacitance here, where there's a frequency dependence that at very low, at high frequencies, the capacitor cannot respond fast enough. It's not going to act as a capacitor. And you could visualize that as a connection shown here. So at infinite frequency, you can approximate that this capacitance will be down to, reactive capacitance will be down to 0, or the relative resistivity that the electrons are seeing is down to 0. And you can view that as a connection between the two plates of the capacitor. Or if you're at very low frequencies, the capacitor can respond, that charge will build up on one of the plates of the capacitor, and you can view that as infinite resistance based on that reactive capacitance equation here. So that's why, depending on where the capacitor is placed, you can see at high frequencies, the charge will be able to pass through and connect to ground. So that's why high frequencies would be removed from the RC filter for a low pass filter if the capacitor is passed there. But at very low frequencies, it will build up and it will actually pass to the output shown here. So that's the physical reasoning behind the response of a low pass filter and the high pass filter here. We established what the instrument response function is for the low pass filter, that it'll have a Lorentzian type shape. So if we plot that in the frequency domain, it'll look like that half of a Lorentzian shown here, remembering back at a past lecture that a Lorentzian does differ from the Gaussian bell curve type shape. And if we plot that on a log scale shown here with decibels for the output, you'll get this characteristic shape for your frequency response function, where we're calling with the decibels how that, and the log base scale of that, how that affects how much change in power you're seeing. A change in 3 decibels is half the power, or 1 over the square root of 2 of the voltage that you see. So we established that for the frequency response function, and then knowing that the instrument response function is the Fourier transform of the frequency response function, the Fourier transform of the Lorentzian curve is an exponential. So that's what you would see for your instrument response function in time, where your time constant would be your cutoff, where you would see 1 over E drop off in your output signal. And the frequency response function, because they're conjugate variables, is the inverse of that, where you would see a drop off of 3 decibels. And then finally, we discussed the phase shift for a low pass filter, defining as the arctangent of the frequency times the RC value, giving this type of plot here. So very quick condensed overview of the low pass filter. We're going to do the same with the high pass filter and the band pass. So the high pass filter, you flip where the resistor and the capacitor are located at. And since it's just that flip, then quantitatively, we can also take that as the inverse for the high pass filter with our voltage response, our instrument response, our frequency, our phase, and the like. So it's 1, where this 1 represents a constant here, minus the response of a low pass filter. Same with the frequency response here. So we could switch that as a flip of the Lorentzian for the frequency response function. Also could plot that as on the log scale, where again, it's flipped. So it's important to know when you're dealing with high pass and low pass, keeping these things straight of what direction you're seeing the slope in the log scale. Again, you define the frequency cutoff or the time constant as the same as RC, or 1 over RC. We defined the instrument response function if you're taking the Fourier transform of some constant and also the Lorentzian. The constant shows up as a delta function at very fast timescales or low or high frequencies, and then exponential growth here for the Fourier transform of the Lorentzian. And then the phase is again the inverse or the flip, where you're seeing no phase change at high frequencies. This is how you'll keep it straight. High pass filter, high frequencies won't be modified, so you won't see a phase shift. 45-degree phase shift right at that cutoff frequency, and 90-degree highest phase shift change at the low frequencies that are going to be modified the most by your filter. And then finally, for this quick recap through PowerPoint, we also discussed the bandpass filter, how it's an LCR, where again, the capacitor is going to block low frequencies based on where it's located at here. And the inductor, introducing that inductor will block high frequencies, so you have a band. And we're defining our quantitatively the center of the band as omega naught, which is 1 over the square root of LC. And then the width of your band will be related to this will be how you define the quality factor of your bandpass filter, where that's going to be related to the center frequency and the width at the full width half max, and that's going to be the L square root of L divided by C, all divided by R here. So those are important ways to quantify your bandpass filter. And you can go in the Phys 122 labs to remind yourself of the frequency response of a bandpass filter. And then you can also, again, take the Fourier transform to get the, of this characteristic shape here, of this equation, if you want to get quantitative about the instrument response function, but this doesn't have a defined shape here. This is not a Lorentzian type shape for the frequency response. And then that the phase response, we just wrote this equation out showing that near your center band, where your signal is passing through the most, if we go back to this little sketch here, where your signal is passing through the most, you're going to have the minimal change in the phase. So theta equals 0 here at that center frequency, omega naught, and then you'll have positive or negative changes above and below that frequency, where here the center inflection point is going to be omega naught over here. So any questions with that quick recap of all the filters?
Could you please go back to the Fourier transform graph of the high pass filter? I think it was on like the first slide of it, maybe.
This one?
Yeah, so and could you so what's the difference between this one and the low pass? Is it just the spike?
Yeah.
Okay.
And then it's also flipped. So if we go back. So yeah, you see this exponential decay over here that again, going the wrong direction. Yeah, so you'll see an exponential here. This is a growth reaching to 0. So it again is inverted with the addition of this delta function as well, due to that constant.
Thank you.
Yeah. Any other questions?
Yeah, just one quickie. So when you're calculating delta omega, you said that's the full width half max. Is that for a dB scale, or is that just for like a regular linear scale?
I think that would be on the linear scale, but I will double check and make sure with that. Delta omega. Yeah, and part 4 of lab 3 also gets into that with some data I provided. Any other questions? Okay. So we'll get into some new content now. That I think most of you guys got through part 2 of lab 3, and tomorrow